Hi guys, I just wanted to make a video just so we can get through what we need before your exam. So let's have a look. The first part of this topic you'll be familiar to some of it from Year 11 Advanced when you first started looking at differentiation. So the first lesson, I've just got a summary on the first page here when we're looking at displacement, velocity, and acceleration. So displacement is the position of, let's say, a particle, where it is. Velocity, it's not the exact same thing as speed. It is speed, but it has a direction, so either positive or negative. So that's a key thing to know there. And acceleration it's the rate that the velocity is changing, okay? So some notation. Displacement we often represent with an X. Velocity then can be a V, but more commonly you'll see it with an X with a dot. And then acceleration X double dot. And you'll notice down the side here, the derivative of displacement is velocity. So, we're putting a dot there instead of the dash that we normally do for derivative. So then the derivative, the second derivative of displacement or the first derivative of velocity is acceleration. It also works backwards now, we can integrate. So the integral of acceleration, velocity, and vice versa. Some little important tips. When you hear the word initially, that's at time equals 0. When we're talking about something being at rest, okay, it can be at rest and have a displacement. So your car can be at rest down the road. It's got a displacement. But you aren't moving, right? So there's no speed, there's no velocity. So at rest means velocity is 0. And don't forget, when we see the word rate, it means derivative. So when it's asking you to find the rate of change, it's talking about the derivative. Some other things to know about what they like asking in a HSC is, they like you to comment on what's happening to this particle, depending on, what the acceleration velocity are doing. So a particle will always be speeding up if the velocity and acceleration have the same signs. Okay, so that's what this first little summary here is saying. Even if the velocity is less than 0, okay, that just means it's traveling in a negative direction. As long as then the acceleration is also less than 0, then it's speeding up. Same thing, if they're both positive, speeding up. But if they're opposite signs, so one's going one way, the other's going the other way, then it's going to be slowing down. So another important note for your questions. Okay, so first thing we're going to look at is rates of change. So again, as my summary up here said, that rate, remember, it means derivative. So the derivative dy dx is a measure of the rate of change in many practical applications. The rate of change we can look at, in this particular case, the population of a city with respect to time, we'd be dp dt, okay? If we were to talk about the population itself, then we're looking at that would be the initial value, and I'll just fill in what we need in this box here. So if I'm looking at dp dt, this is the So we're looking at the changing population over time. Sorry, I'll try and get a bit neater. Okay, so first example, the number of bacteria in a culture increases according to the formula here, all right, where T is time in hours. Find the initial number of bacteria. Now you can pause this video anytime if you want to just give the questions a go and then check your answers. Remember, initial means that T equals 0. So I'm going to show my working. and I get 2,000. And therefore, and you know, putting it back in a worded answer because it's a worded question. All right. We get 2,000. The number of bacteria after 5 hours. So I'm going to say, well, I know that's when T equals 5 because it tells me that T is time in hours. So again, subbing that in. And getting my answer there. Then I won't, hang on. I will get my calculator here, just check that answer. There we go, 3225. And again, another therefore statement. Okay, the rate at which the number of bacteria is increasing after 5 hours. Notice the key word here, rate. So we're going to find the derivative. We're going to be differentiating B with respect to T. All right, my derivative would be 8T cubed minus 2T. So now I sub in at T equals 5. $9.90. Now this is a rate, so we're looking at, that's how many bacteria per hour. When something asks for the average, so we know that the derivative finds us the instantaneous, but if we want to know the average, that's where we're looking at our good old y2 minus y1, so 2 points. So basically we're finding the gradient between those 2 points. So it says the average rate of change over the 5 hours. So what do we know? Well, initially when time was 0, so I'm writing this in terms of T and then bacteria B, there was 2,000. So that's my first point. And then I know that when T was 5, I had 3,225. That's my second point. So now I just sub that into my formula. Doesn't matter which way I put which point, as long as it's consistent. And get my answer. And I get 245. So again, that's a rate, so back per hour. Okay, so let's keep moving on. If you want to pause the video here, give these a go. And otherwise, I'm going to I'll give this first one a go. My solutions that I'll upload in the booklet, I'll also have the second one done as well. But let's see how we go with this first one. Again, pause if you want to. Okay, initially, so again, T equals 0. This is V equals. And putting it back in its terms, so this is volume in litres, so 25 litres. Okay, after how many seconds will the cooler be quarter full? Well, if it initially had 25 litres in it, I want to know when it's going to have 25 on 4 litres in it. And so rearranging this for T. So divide through by 25, it's just going to give me 1 on 4. Take the square root. see what I get. Now, obviously, you can see that I'm working this out, as we go through this video. So if you notice any errors, there could be some here for sure. What have we got? 1 plus a half. So I've got 90. But then if I do 1 minus a half, I'll have 30. So we got two answers here. So 90, and these are what, seconds? And 30 seconds. Again, I would normally write a therefore statement, so put one in yours. Let's just go to part 3 though. At what rate, there's our word, was the water draining when the cooler was 1/4 full? And one thing to note, it's given us a domain here between 0 and 60. So therefore, it's when t equals 30, because 90 would be out of my domain. Okay, so part 3, rate. So what does that mean? Derivative. Let's see. If I do v dash, I get, or dv dt. Times by the derivative. And that wants to know at, well, we know that was 1/4 full at t equals 30. Was time in seconds? Yes, it was. So I'm subbing in 30. Which would give me 1 minus a half. Gives me a half, so -5 on 12. Which makes sense because it was draining out, and that is what, liters per second. All right, as I said, I'll put up the solution to this next one, but definitely give it a go. It'll appear in my booklet solutions on OneNote. Let's keep going though. Now we're going to get more into the motion. So displacement, velocity, acceleration. I'm going to go fast through this next part because it's all been summarized on that initial page for you. Okay, if the position of the particle is to the right of the origin, the displacement is greater than 0. If it's to the left of the origin, it's less than 0. And if it's at the origin, it's equal to 0. Okay. The velocity, so again, we can represent that usually with x dot or v, but more commonly x dot. If the velocity is greater than 0, it's moving to the right in a positive direction. Because remember, this is all two-dimensional, okay? Velocity is moving, it's less than 0, so it's going left in a negative direction. And if it's 0, it's at rest. All right, acceleration. So this is where we could say it's x double dot, or technically we could also say it's, if I write it the long term, I always get this mixed up, d squared x over dt squared, the second derivative of displacement. If the acceleration is positive, the particle is accelerating to the something. Think of it pushing to the particle to the right. So if the acceleration is positive, the particle accelerating to the right. And if the particle is accelerating negatively, think of it going to the left. When the acceleration is 0, the particle, think of it as not pushing the particle anymore. So this is called a zero acceleration or a constant velocity. And think, if something's traveling at a certain speed and then you're not accelerating, that means you're not going to be changing that velocity. So it's going to just stay the same speed. So this is where we're looking at this next part, what we had in this little summary here. So remember, same signs, speeding up, okay? Same signs, speeding up. If the acceleration is just the same direction of the particle will speed up. Opposite directions, slow down. All right, let's get into a question. What is the initial velocity of this particle? So it's giving us the displacement for time t in seconds. So the initial velocity, I need to find x dot and then sub in t equals 0. Again, pause the video if you'd like and give it a go yourself. And what are we? Meters per second. Okay, at which time is the particle stationary? So stationary means at rest. So that's where x dot is equal to 0. Notice how I'm telling the marker I know that. So now I'm solving 0 equals t squared. It's a quadratic. Let's hope it factorizes nicely. I think it will. There we go. And lastly, find the position of the particle when the acceleration is 0. So position means displacement, but I don't know what time it's talking about. So I need to know what time the acceleration equals 0. So let's find the acceleration first. Acceleration, I need to differentiate again. There we go. I know what the acceleration is 0 when time is 2 seconds. So now I can sub in that. And let's see what I get. Two-thirds. Now it's a positive answer. So what we like to do when we're talking about displacement here, so it's 213 meters, we'd say to the right of the origin. If it was a negative answer, then we'd say to the left of the origin. Okay, give this next one a go. I'll pop up my booklet solutions with this in it. Let's just have a look at a couple of motion graphs. So it says this graph shows displacement of a particle as it moves in a straight line. So this is the position of the particle. And we've got time on the x-axis and displacement on the y-axis. When is the particle at rest? Remember, at rest means where the first derivative is equal to 0. Okay? So we know that when we're looking at a graph, the first derivative is equal to 0, that's the gradient is 0. So I can read straight off there, that's my turning points. So I say at T3 and T5. When is it at the origin? So that's at the origin means where the displacement is 0. And that just means my x-intercepts. So T2 and T4. Now the greatest speed, so that's wanting to know, well, when is my first derivative the greatest, okay? So a few things here. Initially you're looking at, okay, when is my gradient the steepest? So looking at that, let me see if I can get a highlighter here. Greatest, so when's it the steepest? It's hard to read off this. What about if we draw the derivative of this graph? I'm just going to do it here underneath. So I got here, I got all positives, negatives, positives. Positive above, 0 negative. Okay, so it's infinitely above, then it's below, and then it goes above again. So when is it the greatest? I would be saying it's hard because you can have a negative velocity that could be still going as fast. I'm going to go with my initial thoughts. I'll double check this. It's greatest when it's going to be positive, because there's no other way we can read off this. We can't find the instantaneous rate. We don't know the equation. So let's go when T3 is less than 0. Oh, sorry. When x is less than T3 and when x is greater than T6. I'll double check that and have it in my booklet solutions. But otherwise, give these next ones a go, all very similar. And then you've got exercise 8.12. See how you go with it. I'll make a separate video for the next part, the exponential growth and decay. And you guys can watch that. I'll post it in the Teams when it's ready.